This video was brought to you by Hexagon. We know how to get to the moon. We've known that for over 50 years. But staying there is a completely different problem, because out there, nothing protects you. One moment, the sun is over 250 degrees Fahrenheit. The next, you're in darkness below -200.
Hi, I'm Travis Egan of AMT. I've been in manufacturing for over 25 years, and one thing is clear, that when you're building systems to keep people alive, there's absolutely no tolerance for guesswork.
The problem is, none of that gets solved up there. It gets solved over 200,000 miles away, down here. In this episode, we're stepping inside that system, a chain of decisions that has to hold when nothing else does. At the center of that system are companies like Paragon, designing the environments that make human life possible where it shouldn't be. Some of the most important engineering in space doesn't happen in space at all. It happens here, in Houston. Just minutes from NASA's Johnson Space Center, Paragon has spent decades developing systems designed to keep astronauts alive, and solving the challenges of living and working in space was something we'd see throughout this episode, especially at their headquarters in Tucson, Arizona. But before we could understand how these systems are designed, tested, and manufactured, James Schuler, Director of Operations at Paragon, wanted me to experience firsthand what they were built to overcome. That's right, I got to strap into a real astronaut suit.
This experience has given me a much deeper appreciation of every small detail.
And don't let it fool you, this wasn't easy. It took nearly 25 minutes and a team of 3 people just to get me inside. And by the time it was done, I was completely exhausted.
It comes down to the stitching, it comes down to the pressure, and this is one element of the life support. If you think about what it takes to put people up into space, every small actuator, valve, every component of every piece of every system within that larger spacecraft, everything has to be perfect. Everything has to be of the highest quality. There is no margin for error.
While Paragon's work today spans everything from life support systems to environmental controls, a lot of which we'd explore later at their headquarters in Tucson, the company has spent decades developing spacesuit technologies as well. Their expertise ranges from pressure, garments, and glove systems to complete life support integration, engineering every layer, joint, and interface needed for astronauts to survive in some of the harshest environments imaginable. That expertise helped support Alan Eustis's record-breaking StratX mission, where he jumped from an astonishing 135,898 feet, setting the world record for the highest freefall jump ever completed by a human, a record that still stands today. Today, Paragon is helping shape the next generation of spacesuits, developing the technology NASA plans to use for future Artemis missions, and eventually, humanity's return to the moon with an eye towards Mars. The suit itself is an engineering marvel, but it's really thousands of smaller engineering challenges. You don't engineer a spacesuit. You engineer every piece of it.
So I see over here on the wall something as simple as these are the fingers?
Yes, yes. So,
the wall of fingers?
So various materials, various parts of the glove, whether that's for dexterity, radiation, heat shielding, insulation, mobility, all of those things have to be factored in. So as we look at this, wall of glove fingers here, each finger has a different purpose in dexterity. And so each finger has its own pattern, its own capability that has to be considered when
so it's customized to the individual needs of the individual finger.
Absolutely.
So these are all different types of fabrics that you would be in a spacesuit?
That is the layout of actual material used in the EMU spacesuit that is on station currently.
Really?
Mm-hmm.
So this would be the outer layer?
That's the inner layer.
Inner layer.
That would go up against the bladder or
Okay.
the pressure garment.
Yep, I was just experiencing
Yep. And those are layers of mylar.
that. Multiple
Yep.
layers of
Yep.
mylar. All the same, more or less?
They're all
or?
the same layers. It's just different levels of warmth and security
Okay.
from radiation. It has this
Pattern.
on here, which helps for thermal,
Mm-hmm.
so that they're not like smashed together.
Yeah.
You help
Creates
use your air.
like a pocket.
Keeps air gap there.
Yeah.
And then the outermost layer is your orthofabric, which is what you see. And that is made of Kevlar,
Very true.
Teflon, PTFE.
Very inexpensive fabric, I'm sure.
Absolutely.
It's a color type so that you could see it against the moon and the black of
Yeah.
black.
Yeah.
Interesting.
So and that's a requirement for a spacesuit so that
Yeah.
it can be seen.
It's interesting. Every little detail is engineered.
Every part of a spacesuit is designed to protect astronauts from an environment that's constantly trying to kill them. Sometimes those threats are obvious. Others, you might never think about.
So inside here we have the Lunar Regolith simulant, and so these gloves are a little tight to get on there. It's an experiment we're doing to try and figure out how best to get the regolith off of everything it touches. As you can see, there's anything that comes in contact, it sticks to. It's very challenging to get it to disperse, to get it off.
Unlike dust here on Earth, lunar dust has never been shaped by wind or water. Instead, billions of years of meteorite impacts have left it with sharp, jagged edges, making it behave more like microscopic shards of glass than ordinary dirt.
And you say that this would be, if I had held this in my naked hand, it would cut me?
It'd tear you up pretty badly.
Yeah.
Yeah. So you're talking almost like a powdered glass. It's very destructive to most fabrics. It's one of the reasons why we test with it, is because you get to see just how caustic it's going to be to the spacesuit in a controlled environment.
It didn't take long for NASA to realize just how unforgiving lunar dust really was.
Everything's getting awful dusty. Everything is just full of dust.
After the Apollo missions, astronauts returned with visible wear on their suits, especially around the knees, where kneeling on the moon had ground the abrasive dust directly into the fabric. And it has become something that every component built for the moon must undergo thorough testing for.
And although this regolith is very similar, it's not like the real thing. It's about as close as we can get or replicate on Earth, because regolith is obviously, it's in short supply. We haven't been to the moon in some time now, so most of it exists probably in NASA's control, but we can't get access to it unless we're contracted to do something.
Yeah.
But with the regolith here, we can get the simulant, which gets us pretty close. It gets us to an environment that allows us to help engineer and overcome challenges associated with it. So being able to disperse the regolith off of fabrics, off of metallics, things like that, any of the structures and things you might be exposed to, as you can see, it's stuck to that glove. So cleaning that off and being able to get
off.
it's not not easy to deal with, for sure.
Extreme temperatures, abrasive dust, and the realities of living off Earth influence every engineering decision. It's why Paragon's work extends far beyond the spacesuit.
So now that we've seen sort of the survival system itself, the life support system itself, the next is to look at the larger ecosystem of life support in Tucson.
Absolutely. Can't wait to take you there.
I'm ready to go. I'm gonna take this off first.
Sounds like a good plan.
When most people think of America's space industry, they think of Houston or Cape Canaveral. But hundreds of miles away in the Arizona desert, another aerospace hub has been quietly helping shape the future of human spaceflight. It's here in Tucson that Paragon designs, prototypes, builds, and tests many of the life support systems being developed for NASA.
Good to travel into here. This is our wet lab. So this is our brine processing assembly. And so we've actually had this hardware on station. This is operating, dewatering brine on station. It has been going for about 5 years now. We've just passed, I want to say, our 1,000 or 2,000 liter mark of water recovered from brine on station. So that's water that hasn't had to been shipped to the International Space Station that astronauts are able to use, repurify, break down, use for experiments, or purify further for potting purposes and drinkable water. So this is an ongoing experiment. We've had this technology. It's been in process for well over a decade now. And so this is a refinement of that technology, kind of a proto lab version. And the flight unit, as you'll see a little bit later, is on station. We've got astronauts just did a bladder change out a handful of days ago, where they're taking the consumables out. And it's interesting to watch them don a lot of PPE to get in there and deal with what's normally a very hazardous thing. But they've got smiles on their faces when they're doing it.
Recovering water in space isn't as simple as running it through a filter. Today's systems rely on hazardous pretreatment chemicals to stabilize the waste before it can be recycled. Hundreds of miles above Earth, even a small leak becomes a serious safety concern. That's why every valve, every seal, and every connection has to be engineered with multiple layers of protection.
So how much water can be reclaimed at this point?
98+%.
Okay.
So as you're thinking, hey, we're extracting water, we're constantly breathing, exhaling water, we're sweating water out, urine is a big recapture. And so that's a lot of mass that can be saved, salvaged, and repurified and used for other things.
Is that the best case scenario, 98%?
98% is the requirement for us for long-term space flight for a man to go beyond the moon.
Okay. So you could take water to the moon.
You could.
It's a short enough distance, essentially, even though it's 200,000 miles away.
Yeah.
But you can take the water up there. But if you're going to Mars, you're going interstellar, you have to have the ability to recycle.
What surprised me most wasn't that the technology worked. It was that it had already been quietly doing its job aboard the International Space Station for years. The challenge now wasn't proving it could recover water. It was adapting that technology for longer missions, greater distances, and humanity's return to the moon.
All right, so you've got all these subsystems that you guys develop. This is one example. What are the other critical systems that is developed by Paragon?
Absolutely. So humidity control is a big thing here at Paragon. Not only recapturing water, we have some of our units like our Cosmic unit, which is able to capture water out of ducting. So it's taking centrifugal force and it's capturing water droplets from ambient air. It can be put in line to different pressure systems, and there's zero pressure drop. So the advantage for that is you can take it into existing exhaust systems, retrofit it to older models, and it will be able to recapture that water, create it into droplets, and then that as well can go in for future purification. We have our radiator technology for heat expulsion. We have our cold plate technology for heat recapture and generation expulsion as well. And we're doing some pretty interesting things with humidity controls, which you'll get to see here shortly.
Awesome. So you guys are like the space HVAC guys.
Pretty much, yeah.
It was a funny way to describe it. But these aren't just heating and cooling systems. Paragon is helping build the environment control and life support system, an incredibly complex network responsible for circulating air, regulating temperature and humidity, removing contaminants, monitoring the cabin atmosphere, and helping create the environment astronauts depend on every second they're aboard. It's the next evolution of technologies already proven aboard the International Space Station, now being advanced for the longer missions and permanent infrastructure that will support humanity's sustained return to the moon and eventually journeys even deeper into space. Designing technology like that is one challenge. Manufacturing it to perform flawlessly is another entirely. And what we were looking at today was only one part of that entire system.
This is the fun part.
Yes. All right. So this is the high bay. This is where all of our assembly integration hardware gets both put together, inspected, incorporated into the subsystem to where it can then be brought into the station.
So tell me a little bit about what we have going on here.
Absolutely. So this is the base plate of our air revitalization system.
Okay.
So this is the heart and soul of what is going to be the system that keeps the astronauts alive in space.
So when you say the base plate, is that like the foundation of it and then you build up from there?
Exactly.
Off of it? Okay.
Yeah. So we see a lot of mass reduction features in here. A lot of interface is going to be on the bottom side of the part, but tons and tons of holes that are very tightly controlled for the stack-up tolerance necessary for all the rest of these remaining components to get built up off of this. So we have to build one for flight, one for our qualification unit, and then we always have one for safety.
So you have a backup.
We always have a backup. And in fact, we have one measuring over here if you'd like to see it.
I would love that.
Building hardware for space is never a one-company effort. It takes trusted partners at every stage, from engineering to manufacturing to one final question. How do you prove it's right?
What is the role that Hexagon is playing in helping these guys out?
It's a great question. So, when someone draws a blueprint up and they need a part manufactured,
Right.
you just assume that part comes off the cutting tool or the additive tool correctly, right? And so the role in manufacturing that this machine plays is it checks it out.
Yeah.
Right? And so what you're seeing is the probe coming down and physically touching the part and taking that data back through the software and going, is this component, piece, feature where it's supposed to be based on the blueprint or the CAD model? And that's what you're seeing it do now.
This is Hexagon's global 15.30.10 coordinate measuring machine, capable of measuring parts nearly 10 feet long. And to put its precision into perspective, it can detect deviations as small as just a few microns, roughly 1/3 the width of a human hair, while laboratory instruments can make even finer measurements. What makes this machine remarkable is the scale at which it does it. It can detect a deviation smaller than a single red blood cell across a part nearly 10 feet long. And for the size and complexity of the hardware Paragon was building, James wanted the largest bridge CMM Hexagon produced in North America. It's how they verify that every critical feature matches the original engineering design before it ever becomes part of a life support system.
There have been things where we had no idea how we were going to inspect it. We knew we could make it, but how do you verify it?
Right.
And we've had some very interesting conversations. In fact, I think we were one of the first companies to use the Hexagon RS6 laser scanner almost like a CT scanner. And so we were able to determine a remaining wall thickness on a feature that had experienced some damage and said, hey, we need at least 16 thousandths of material left in this very, very tiny spot. We said, and how can we get in there and figure that out? And we were able to 3D map that with the scanner, use the roamer arm to project a cylinder through that feature, and we were able to calculate it and figure it out.
The more time I spent at Paragon, the more I realized this wasn't just a workplace. It was a close-knit team that genuinely cared about one another and about passing their knowledge on to the next generation. Before we stepped into the machine shop, James wanted to show me exactly what that looked like.
All right, this is my favorite part, the machine shop.
Absolutely.
Let's check it out.
Absolutely. But first, before we do that, I did want to kind of take a moment to reflect on a former Paragonian that we had here. His name was Paul Perez. He was a machinist, dedicated father, veteran, manufacturing specialist, phenomenal machinist, worked 20 plus years in the trade, passed away during COVID. So when we moved into this facility, we took an opportunity to dedicate the shop in his honor, named it after Paul. It's the Paul Perez Manufacturing Center. And so it's very special to us to make sure that we honor those of our comrades who allowed us to be what we are today. This is the shop. It's small but mighty.
Small but mighty.
So here at Paragon, because of what we do, we don't manufacture a ton of anything.
Okay.
Because space is such a niche market right now, what we focus on is our capability.
Yep.
So we have a broad array of machines, but we also have backups for those machines. So you'll see behind us, we have our Haas GR510. Right behind that, we have another one. And we bought that as a backup piece of equipment in case one went down, because in the time we were in the throes of building our radiators. And so this was the only thing at the time when we originally bought this machine that would fit in our building. And so Ricky here is loading up what is one of the side plates of our air revitalization system. And this part is 7075 aluminum, and it's got to maintain a flatness of 20 thousandths across that with a localized flatness of 2 thou across any 5-inch span. And as those of you who've done any 7075 hog outs know that it's not a forgiving material when it comes to twisting and warping. So Ricky's doing a very meticulous job of order of operations and sequencing and shimming just to get this part dialed in, because we're making two. And that's a challenging thing to do.
Is this a production part or is this a prototype?
So this will be part of the flight unit. This is actually
Okay.
going to launch the parts that he's manufacturing currently.
Everywhere I looked, Paragon was solving another piece of the puzzle: manufacturing flight hardware for NASA, machining precision components for next-generation life support systems, developing humidity control technologies, building hardware that will help recycle water, manage heat, and create a habitable environment hundreds of thousands of miles from Earth. Even putting those systems through simulated space conditions, testing them inside vacuum chambers before they ever leave the ground. The technology was remarkable, but looking around the machine shop, it became obvious that building hardware for space isn't just about the machines. It's about the experience behind them, knowledge that's been earned, refined, and passed from one generation to the next. Because, as James explained, once that knowledge disappears, rebuilding it isn't easy.
So why is it that there was such a dip, a lull between when we did that in the early 50 years ago to where we are today?
I think a lot of people have a lot of different ideas about that. Number one is probably funding and the desire to get there.
Sure.
The space race really drove a lot of that. But from my perspective, and what I see as a major contributor to that, is the folks who built the initial systems that got us there, that skill set started to dip. And we lost that capability to build. And there was a lot of secret sauce, really internal knowledge going on where manufacturing challenges had to be overcome. And we weren't documenting very well, and we weren't training the next generation how to do that. We weren't, making sure that that got edited on the engineering drawing in the background. So as that got launched and those people passed away, retired, or got out of the industry,
Sure.
that skill set went with them.
At the beginning of this video, I said we knew how to get to the moon. But after spending time with the people building the next generation of spacecraft, I realized that wasn't entirely true. The science never disappeared, but much of the manufacturing knowledge, experience, and hard-earned lessons that made Apollo possible slowly faded as that generation retired. Recognizing that challenge, NASA launched the Apollo Knowledge Capture Program to preserve the experience of Apollo engineers before it was lost forever, because blueprints alone can't capture decades of manufacturing knowledge. And that's a challenge reaching far beyond Paragon. Across the aerospace industry, a new generation is relearning skills that in many cases haven't been practiced at this scale for decades. For Paragon, that effort begins right here.
And so what we're trying to do is foster an environment where we're growing talent. Because whether they work here at Paragon, whether they work at one of our vendors, or they go to a sister shop in Phoenix, we don't mind as long as the pool of talent continues to grow.
Sure.
And so we work with Desert View High School as well as Pima Community College and their advanced manufacturing curriculum programs as consultants for both their curriculum as to what they're teaching the students.
Fortunately, we got to meet one of the people carrying that legacy forward, an engineering student getting the rare opportunity to learn alongside the same team, designing and building the systems that may one day take us back to the moon.
I've been here for about 2 years now, and in tandem with my schooling at University of Arizona, going for a bachelor's in mechanical engineering.
So when you were, growing up and thinking, I want to get into this field, did you ever imagine that you would be going to college and then being able to come over to aerospace manufacturing company and actually work, a CNC machine like we have this Haas machine here?
Honestly, not at all. This was something that I just got so lucky that fell into my lap through a lot with a club that I was in high school that I was really fortunate that they provided me the opportunity to interview here.
And how do you feel about the space program and what's going on with Artemis and having a chance to be a part of it? How does that feel?
It's really exciting. Growing up, I always saw everything with NASA, and I found it so exciting just to see that we were actually sending people to space. And recently, even with the Artemis 2 launch, I was watching that every single day, checking in and watching all of the interviews with the astronauts, and it was really awesome. And to be able to be a part of something for that is really exciting to me.
A critical part of that too. I mean, the life support systems that those folks are going up there, they rely on folks like yourself, and that's a really exciting future.
After more than 25 years covering manufacturing, I've learned that every great company has impressive machines. But what I found at Paragon was something even more important: a passion for the craft, a culture built on mentorship, partnerships, and people who genuinely love what they do.
Who just know that we have to do the impossible every day and it has to be perfect. And you can't do that if you don't love what you do.
Because the future of manufacturing isn't built by one company or one technology. It's built by people willing to dedicate their lives to mastering a craft and passing it on to those who come next. And if humanity is serious about returning to the moon and one day reaching even farther, that may be one of the most important systems we'll ever build.